How do phonons affect thermal conductivity in thermodynamics? Have you ever wondered how heat travels through materials? One key player in this process is phonons. Phonons are tiny vibrations of atoms in solids, and they are the main carriers of heat in nonmetallic materials. Understanding how phonons work can help us grasp thermal conductivity, which measures how well a material can conduct heat. Thermal conductivity is influenced by three main factors: phonon heat capacity, phonon velocity, and phonon mean free path. The phonon heat capacity tells us how much energy phonons can carry. Phonon velocity is the speed at which these vibrations travel. The mean free path is the average distance a phonon travels before it collides with something. Together, these factors determine how effectively phonons can move thermal energy through a material's structure. When phonons move from hotter areas to cooler areas, they carry energy along with them. The relationship between thermal conductivity and these factors can be summarized in a simple formula. Thermal conductivity is proportional to the product of heat capacity, average phonon velocity, and mean free path. This means that as any of these factors increase, thermal conductivity also tends to increase. However, phonon scattering can limit thermal conductivity. Scattering happens when phonons collide with other phonons, impurities, defects, or boundaries in the material. This reduces their mean free path, making it harder for them to transport heat. There are two main types of phonon scattering: normal processes and umklapp processes. Normal processes conserve phonon momentum and redistribute energy without resisting heat flow. In contrast, umklapp processes do not conserve momentum and act as a barrier to heat flow, limiting thermal conductivity. At low temperatures, phonon scattering is less frequent, allowing phonons to travel longer distances. As the temperature rises, the number of phonons increases, leading to more collisions, especially with umklapp scattering. This can shorten the mean free path and reduce thermal conductivity. Therefore, thermal conductivity often increases with temperature at low temperatures but decreases at higher temperatures due to these scattering effects. In materials like silicon, phonons are the primary means of heat conduction. This understanding is crucial for designing devices for cooling electronics or thermoelectric applications. While metals also conduct heat through electrons, phonons still play a significant role, particularly at elevated temperatures. In summary, phonons are essential for transporting heat through materials. Their effectiveness is influenced by their velocity, heat capacity, and the scattering mechanisms that limit their mean free path. By grasping how phonons work, we can better understand the principles of thermodynamics related to energy transfer and heat transfer mechanisms.